Sequencer instruction. We're supposed to be able to describe the operation of sequencer output, sequencer compare, sequencer load instructions, connect sequencer instructions to increase the number of sequencer steps, and connect sequencer instructions to increase the number of sequencer outputs.
I know this is a very simple way of putting this, but is a sequencer kind of like a Rube Goldberg machine? Like one thing has to happen before the next thing has to happen?
No.
Not like that?
No, sequencer is more of a, we're going to do this sequence of events every time.
Okay.
In this order.
So it has to be step one, then, so kind of like baking instructions, like add your flour, then mix, or whatever. It has to go in that order.
Yeah.
Okay.
You have to add this ingredient first, then this ingredient, then this ingredient. Then you have to mix it up, you put, spray the baker's secret or, butter and flour, the pan, and then pour the batter in, and then you have to go in the oven, blah, blah, blah. There's very specific sequence of events that have to happen. Okay. You have to drill a hole before you can tap it.
I hope so.
It'd be really cool if you could drill it and tap it at the same time.
So they got self-tappers.
Yeah, they also have drill bit. Makes a hole.
Yeah.
First. Okay, sequencer instructions. My whole idea behind sequencers is to control several outputs with multiple step patterns. State of the output device that are connected to the output ports can be changed from on to off or off to on or remain the same. Imagine that. Just like good old ladder. And time between each step can be controlled by output, compare, and load. Time between each step sequence can be controlled. There are three types of them: output, control, or compare, and load. Concept number one, table to register or file to word. PLC manufacturers use instead of the sequencer instruction. Not as versatile and complete as the sequencer. Output patterns that need to be repeated in the manufacturing process are usually set up in sequencer. So in this particular case, you have 3 steps listed anyway: motor 1, motor 2, green pilot, red pilot, white pilot. Step 1, motor 1, motor 2 are on, everything else is off. Step 2, motor 1, motor 2 turn off, green pilot, red pilot turn on, white stays off. 3, motor 1, motor 2 stay off, green pilot turns off, red pilot stays on, white pilot turns on. Why you want to control light bulbs with a sequencer, beyond me, but whatever. Have number of steps, starting register, the step pointer, destination. The number of steps is just how many steps of the sequencer going to do. Depends on how many operations you need to complete your whatever it is you're doing. Starting register is what holds the data that you're going to write into the output register to control the outputs. Step 1 is always your starting register. Okay? The step pointer keeps track of where in the sequence it is. So if it's on, step 3 or step 25 or whatever it is. And then the destination is where you're writing the information that you're pulling out of the source register. Typically, that would be an output register. So enable, enable input must be closed to energize. Step is a low to high pulse on the step input causes the sequencer to advance to the next output pattern. And reset, normally open reset input is closed, sequencer instruction resets to its first output pattern. It also resets the control register back to sequencer block instructions hold 4 blocks of information. The same for the rest of them, step 2. And some PLC manufacturers combine the tasks accomplished by the 3 inputs. One of those companies happens to be Allen Bradley. Names of the registers and their tasks may not be the same for all types of PLC systems. With Rockwell, it is R6 by default. You can create you can create additional control registers and add them, but by default, 6 is the control register. Sequencer output uses 1 input and both enable and step signals. The done bit of the index register or control register is used to reset the instruction, and an input device or a contact used to send the pulse signal low to high to the sequencer output. I don't know why you guys can see it. I'm going to zoom in on that a little bit. Is that better? Okay, so the control register for this one is R60. The done bit is going to send a reset command to, so once it gets through a sequence, it returns back to the beginning. So every time a new part comes in or a new blank or whatever, it can start over and perform whatever operations it needs to and reset. Also, that's your source file, 230. You can use any 16-bit register. So bit file, integer, input file, oddly enough. The mask, you can mask out certain bits that you don't want to go from the source to the destination. You gotta remember how masking works.
Hides it with like a bunch of zeros, moves
Yeah.
put a byte, either the upper or lower somewhere.
Okay, you have some and then if you only want to do, say, those 4, 1, 2, 3, I've got 10 there, I only meant to do 8. There we go. So if you only want to do those 4, you would mask these bits with zeros and those with ones. And then it just does a bitwise and. No, oops. Got used to writing zero. Okay, so this ends up being your source A, that's your source B. So it doesn't matter what these guys are, they'll all be zero. Because anything and zero is zero. Okay. So anything that's ended with a one is just going to be whatever it was to start with. And does that make sense? Control register is just the register that keeps track of where in the sequence it is. Destination is where you're wanting to send the bit pattern. That, by the way, will throw an error when you try to verify your program. Anybody spot the reason why?
Is that just saying like whatever, just the whole number 2 output module? Is that what it's saying?
Mm-hmm. That address is slot level. It has to be a word level instruction. So it should be output :2 period 0. So that's a typo. Length again is just how many steps there are, and then position is where it's actually at. And that position number comes from the control register. Okay. Okay. Signature data file, B3, B10, and 7 just contains the on-off bit pattern or an integer number, which it doesn't care if it's an integer number or not. It's going to look at the individual bits that make up the integer. The reason why it says B10 there is because by default, there are 2-bit files on the SLIC. And this book is written with the SLIC controllers in mind. So the bit pattern there motor 1 is represented by bit 0, motor 2 by bit 1, green pilot by bit 2, red pilot by bit 3, and white pilot by bit 4. You can see how you got the different ones and zeros in there. So step 1, everything's off. And then step 2, motor 1, motor 2. Step 3, motor 1, motor 2 turn off. Red and green pilots turn on. Step 4, green pilot turns off. Red pilot stays on, white pilot turns on. Okay. See how register holds the length of the steps, step position, and status bits. The only status bits that you're really going to be interested in, though, are done, because it's frequently used for resetting the sequencer, and ER, which is the error bit. So if there's an error in your control, it'll flag that bit. And I don't know, sometimes. Sequencer length parameter, the sequencer block, most total number of steps that must be completed before the sequencer status bit done coil is energized. Sequencer position parameter indicates the step that is desired to start the sequencer instruction. So indicates the step that is desired to start the sequencer. It's when it's actually the step that's actually on right now. Ladder diagram for sequencer output. It's a 1 second timer. Every time timer gets done and increments the sequencer. Which on the sequencer, it has to see a false to true transition in order for it to increment. So if this conditional logic continues to evaluate as true, the sequencer doesn't do anything until it sees a false or at least one scan that has that true again, or else it just sits there and does nothing. Compare reads input data from the input modular register, compares the bit pattern with the data file, and the bound bit in control data file R6 enabled if the input data matches one of the patterns in the data file. So you can say that if input 0, 2, and 7 are on when you do the sequencer compare, and in your data file for sequencer output steps 0, 2, and 7. That's what I said, right? Whatever, okay. But anyway, whatever I said, 0, 2, and 7, whatever that was, if it finds that exact bit pattern anywhere in the register, it'll execute that step. Okay, which, again, I really don't know why you would want to do that. I can't think of any good use case scenarios. Ladder diagram using compare. So if when T4 0 is done, let's compare with B3 0 with a 16-bit mask. It's going to be looking at input 1/0. So the bit pattern it's looking for is just one bit, which is kind of silly. All that does is turn on the green file that, so why not just write the logic so input 10 is on the green file that turns on. What do you have to do is signature prepare for that?
Because you can.
Okay. Compare instruction data. That's just a bit pattern that's going to write from there into the signature output. Okay, sequencer load, this is one that you can actually sort of make a case for. If you have a system that you're trying to teach, you can say, hey, when these inputs are on, I'm going to record that status of all those inputs into whatever source file, maybe B3, 7, whatever. Change them again to whatever they need to be, record that, change them again, record that, and so on. So as it's stepping through, it'll turn on and off the appropriate outputs. You have to be really careful though whenever you're doing recording the inputs, because if they actually other things other than what's going on in the sequencer, you can potentially do bad things. Available for 502, 503, 504, 505 in micrologics. Not available on the old SLIC 500. Ladder using sequencer load. So every 60 seconds it looks at the status of input 10 and sets it. Cascading sequencers. PLC applications require the number of steps to be more than 256. That is the maximum you can have on any one sequencer, so you can create 2 of them. When the first one gets done with its 256 steps, the done bit will set, which will enable the second one so they can continue to step through. That would effectively double. Yeah, it's cascading. So when first sequencer gets done, that's the done bit. So that will evaluate as false, effectively turning that sequencer off. That will evaluate as true, effectively turning that one on. Then when the second one gets done, it just resets both of them. So you can start over. You wouldn't necessarily need, it shows here, the length is 100. It'll give you a total of, what, 399, 56 steps. I guess it'd be 357 because you had 0 with both of them. Parallel sequencers sometimes need to control more than 16 ports at the same time. So you can connect them in parallel, so they both operate simultaneously. The same timer done bit and actuate both of them. First one's going to write its output from B30 into output 2, which that's also a typo. That should be a period, not a slash. That should be a period, not a slash. But same length. It's interesting that they drew it with them in different positions. Or only way for them to stay in sync with each other is if they're both on the same step. So if that starts at 0 and that starts at 1, you're going to be off as it steps through. So contents of bit file 3, contents bit file 10 for the parallel or the cascade. And that's it for that slideshow. So now you know everything there's to know about sequencer, right? I said if it's an operation where you're doing, you know, same thing over and over and over and over and over again, it's always the same step. Like one of the machines that they make over at Custom Powder, where I came from, is a blender, a tunnel blender. They put a IBC animated bulk container in there. Push the start button. First thing he has to do is clamp. So always clamp. Then the tumbles, whenever it's done, you can either set it by tumble by time or tumble by revolutions. When it's done, it will look for the home switch so it bends upright. When it passes that, it will decelerate so it comes to a stop when it gets to the top again. You can turn on load leveling so that it goes a little bit past the top, turns around, comes back, so that your stuff's not sitting in the bin like this whenever you get done. Then has to unclamp, you know, so you get all those steps that you have to follow. But it's always the same every time. Clamp, blend, decel, position, stop, unclamp. And then take that fan off, put a new one in, clamp, blend, something, right? They don't program the machines with sequencers, but they could easily do that and, you know, simplify the logic quite a bit. The problem with sequencers, though, is not everybody knows how to read them. So if you have your logic that says when you finish step number 1, you move to step number 2, and step number 2 operates these outputs and blah, blah, blah. If you write that in ladder, it's really easy to follow. If you write it using a sequencer, all it is a bunch of data files. And it's much more difficult to wrap your mind around the logic that is doing the actual control. Okay, so they definitely serve the purpose, but for the average Joe technician, you can really jack with them if you start programming your stuff with sequencers. But I don't see no logic going on here. Okay.